AP Chem Topic 2.1, Types of Chemical Bonds. So let's think about it. In thinking about the type of chemical bonds, you need to consider two things. Number one, the type of elements involved. Number two, their electronegativities. So let's look at those things that contribute to the types of bonds. First type of bond that we're going to think about is ionic. An ionic bond is made of a metal and a non-metal. So if you remember your periodic table, you have metals on this side, nonmetals on that side. The metal will give electrons. The nonmetal will take electrons. That sets up charges. So for example, sodium gives away one electron to be +1. Iodine gains one electron to become -1. Those pluses and minuses then attract each other, and it is that attraction that forms your ionic bond. The next type of bond we're going to think about is metallic, which will have one or more metals. This bond is held together by a free-flowing sea of electrons. So you're going to find one or more metals, which are found here in this metallic bond. The nuclei are fixed into place, and then the valence electrons delocalize and can flow throughout the material. That is what gives metals its properties. We'll talk about that more later. I will tell you now that this makes this conductive. Covalent bond is made of two non-metals. The electrons are shared. So for example, in this cartoon version of a covalent bond, both chlorines are sharing two of their valence electrons, and that is a covalent bond. There are two types of covalent bonds, and that relates to the electronegativity. As a reminder, electronegativity is essentially a measurement of how close to the nucleus electrons will be when they're shared between two atoms. So let me clarify that a little bit. The higher electronegativity values, and fluorine has the highest value on the periodic table, will pull the electrons closer to their nucleus than it will if it's bonded with something that has a lower electronegativity. Okay, so what I mean by that, if you have an Fi bond, the electrons are going to be held tighter to the fluorine nucleus than they are to the iodine nucleus. And if you want more of a discussion on that, you can go back to my periodic trends video. But because of this sets up an uneven balance of charge in the molecule itself. That creates what we call partial charges. So a covalent bond is made of two nonmetals and electrons are shared. And so for this polar covalent bond, the electrons are shared unevenly, which is due to two nonmetals having different electronegativities because they're spread far apart on the periodic table. It's generally how you recognize that. One important note here that carbon has 2.55, hydrogen is 2.20. We recognize the CH bond as being non-polar, even though they're spread far apart on the periodic table. That's more because hydrogen is a little bit strange because of its very small structure, and so it doesn't really fit nicely anywhere on the periodic table. So then if you have a nonpolar covalent bond, that is a situation in which the electrons are shared evenly. And you can have that when you have two nonmetals with similar electronegativities or the same. So you can have that as well, especially when you see a diatomic element like oxygen. Finally, I want to point out to you that while we separate these into four different categories, this is actually a continuum in differences of electronegativity values. So ionic has got the largest difference in electronegativity, and it's so large that we see that giving and taking of electrons instead of sharing. Polar covalent would have some amount of ionic character, so this is a continuum. And then it would keep going until you end up with this situation where you have no difference or low difference in electronegativity values. And then in metallic, we don't even really consider electronegativity there because we have this full delocalization. So they're not sharing, they're not giving or taking. It's kind of this, a little bit of a free-for-all. So if you kind of want, it is a little bit of sharing, but it's different than a covalent bond. There you go.